gate. NOR is a complement of OR gate. It is a combination of NOT gate and OR gate. When you observe the truth table, you get only once, that is output is high when all the inputs of NOR gate are 0, then the output is 1, otherwise 0. It is exactly the complement of OR gate. Then today we start with next gate, that is NAND gate. NAND gate. When you observe this, name of the gate NAND, NAND gate. Again, we come to know that this gate is also the combination of two basic logic gates, that is NOT gate and AND gate. That becomes NAND gate, right? If you observe the logic diagram here, say 2 input NAND gate, D is there, D shape, then NOT gate is connected here. The bubble is added here, small circle. Either you can add this or else even if you split and write complete that NOT gate also okay. But normally we'll write only bubble. We'll miss that triangle. Right? No need to write that. If you add this bubble at the output side, it is enough. Whatever the input we are giving for this logic symbol, it takes and it performs first AND operation, then it performs NOT operation. It means, what do we know that AND gate performs logical multiplication. When that multiplied value is given as input for NOT gate, then the output from that what we will get is the product of that same thing is complemented form. So we'll see now in detail, right? We'll go by first explanation part. See here. A NAND gate takes 2 or more input signal and gives only one output signal. So this is dialog point. Yesterday in the last class also, I was giving this sentence for all the gates except that NOT gate is different. A NAND gate takes 2 or more input signal and gives only one output signal. And the second point, the NAND gate is complement of AND gate. NAND gate is the complement of AND gate. Then connected to the truth table, we have one point here. That is, the output of NAND gate will be 0. The output of NAND gate will be 0 only when all inputs are 1. When all the inputs of the NAND gate are 1, then only the output will get it as 0. And the output will be 0 if any input represents zeros. Then next, NAND is a short form of NOT and AND. NAND is a short form of NOT and AND. The symbol is used to represent a NOR operation, that is, so x dot y can be written as x NAND y. Right? X NAND y. See here, if you observe here, one point will be the clearance we need. Okay, it is correct only. Now, see here. The truth table. So in the truth table, what we need is some changes we need. See, x is there, one input, y is another input. If you observe here, So in the diagram, A and B are given. In the truth table, you can consider instead of A and B, I will take it as X and Y are the two inputs, and X dot Y whole complement will be the output I will take, right? So here instead of this, we'll take it as you don't want this, right? So we'll remove this, then we'll write that. Wait. So here we'll take now that one input is X, another input is, we'll take it as Y. X and Y are the two inputs, and the output we'll get is X dot Y whole complement you will get. X dot Y whole complement. So now you can trace it now. See here, we're taking here, we'll take 1 point. We'll make here also that complement form, then it'll go there. See here, X and Y are the two inputs. So X is 0, Y is 0. Take it here. X is 0, Y is 0. This is the AND gate first. So what the AND does? Logical multiplication. It means X dot Y you will get. What is X dot Y? 0 dot 0 is nothing but 0 by postulates we learned. So 0 dot 0 is 0. That 0 is input for our NOT gate here. This bubble. 0 is input for NOT gate. That is X dot Y value is X dot Y is input for this NOT gate. Then the output what we will get is X dot Y complement. It means 0 complement you will get. 0 complement means 1. That's why if you observe here, when X is 0 and Y is 0, X dot Y whole complement will be 1. And check out the second one. Second combination of inputs. X is 0, Y is 1. See here, X is 0, Y is 1. And yet, logical multiplication, X dot Y. X dot Y means 0 dot Y. Logical multiplication will get 0. If that 0 is input for NOT gate, X dot Y value is 0, that is input for NOT gate, then what will get? Complement of that. That is nothing but 0 complement is 1. That's why the output is 1 again. Then we'll go for third input, that is reverse. X is 1 now, Y is 0. X is 1, Y is 0, and gate performs logical multiplication. So 1 dot 0 is nothing but 0. If that is input for the NOT gate, that is X dot Y complement becomes 0, complement becomes 1. That's why the third output is also 1. Now check out the fourth output. X is also 1, Y is also 1. It means both the inputs are 1, 1. In case of two input NAND gate, see, X is 1, Y is 1, AND gate 1 dot 1 is 1. If that 1 is input for NOT gate, then we'll get complement of that. That is 1 complement. X dot Y complement means 1 complement. 1 complement is nothing but 0. That's why the output is 0. So by seeing this, you can say that when all the inputs are high or 1, then the output is low or 0. Otherwise, 1. Is it clear? The impact statement what we are getting? When all the inputs of NAND gates are 1, then the output is 0. Otherwise, 1. So this is about the NAND gate. Next. Next gate what we will get is XOR gate. It is also called as exclusive OR gate. An exclusive OR gate takes two or more input signals and gives only one output signal. Again, dialog point. Except NOT gate, because NOT gate is taking only one input and it produces only one output. Other than that, we can write this sentence as one point in the gates. The XOR gate takes two or more input signals and gives only one output signal. Then the next point. The XOR gate is different form of OR gate. It is a different form of OR gate only. How different it is? See here. The exclusive OR gate produces output 1 for only those input combinations that have odd number of ones. Again, the output of this XOR gate directly depends on the inputs. What type of inputs we have in this gate, right? Depends on input. If the number of inputs have odd number of ones, it means we are concentrating here only on ones. How many ones are there in the inputs? If this contains total after counting the input ones, if the total is in odd number, then only you'll get the output as 1. The output is 0 if there are even number of ones in the input. And the second case is if the output is 0 means when you get output 0, if there are even number of ones in the input, then the output will be 0. The next point related to table only, that is the output is 1 if there are odd number of ones in the input, that you have studied already. Then the Boolean algebra, circle and a minus sign, just like a diameter, right? Sign stands for XOR operation. Thus, X, Y, if you write, right? X XOR Y can be written as this form. X XOR Y can be written with the help of this symbol. That is, this symbol represents exclusive OR gate. Then the XOR gate has the symbol similar to OR gate. Logic symbol is similar to OR gate. Only small change is there, except the additional curved line of the input side. If you observe here, if you remove this particular curve, say I'm showing this here. In the logic symbol, if you remove this particular curve in the input side, this becomes OR gate. That's why I said that this point, the XOR gate has a symbol similar to OR gate, except the additional curved line of the input side. This is the only extra thing. If you put this curved line in the input side for OR gate, that becomes exclusive OR gate. Right? That can be written as plus sign. That is a circle. Inside that plus you can write, that becomes the sign for XOR gate. This sign is slight, that one more vertical line is missing in this. Here it is correctly, it is written here, right? Printing is correct here. Here misprinting is there. Then you observe now, after knowing that, see here, the exclusive OR logic symbol for 1 marks also. Sometimes this is asked in the exams. Write the logic symbol for exclusive OR gate or XOR gate for 1 marks. So for OR, you can write one extra curved line in the input side, that becomes exclusive OR. If A and B are the inputs, then the output will be A XOR B. This not symbol is nothing but exclusive OR. It means for plus we are circling. Only plus means OR. For plus you can circle that, that becomes exclusive OR. Then the main thing in this is truth table. If you observe that carefully, see here. One column we are writing it as extra here. For what purpose? We are counting the number of ones present in the inputs. For that purpose, you have written here number of ones column. Remaining is same. Only ORs you can write. That is three columns. One input is X, another input is Y. Then the output is X exclusive or Y. Can write plus and circle here. The same, this symbol. Right? We'll get this here. I'll mark that. If you get confused, it is a problem. This is plus symbol is there. Right? Plus. Now, if you observe here, X and Y are the two inputs. Now, first case, what are you taking normally? Both are 0 zeros. How many ones are there in these inputs? No ones, but inputs are 0 evens. Ones are nothing here, dash. No need to write even here, right? Dash is there. There is no ones. It means the output is 0. Then, if you count this, one input is 0, another input is 1. How many ones are there in these inputs? Only one. One is an odd number. So we are writing odd. If the odd number of ones present in the input means the output is 1. That is high. Check out next also. Now this time reverse. X is 1, Y is 0. How many ones are there in the inputs? 1. What is 1? 1 is even or odd? Odd number. Odd number means again the output will be 1. That is high. Now check here. X and Y both have inputs 1, 1. X value is also 1. Y value is also 1. How many ones are there in the inputs? 2. 2 is even or odd? 2 is even number. So if it is an even number of ones present in the input means the output will be 0 or low. Is it clear? Now, I hope you understood this. Same sentence are given here. See, once again, if you revive this, see here, the exclusive OR gate produces output 1. When you are getting 1, see here, only when for only those input combinations that have odd number of ones. See here, odd number of ones. How many ones are there? 1 odd, 2 odd. For that 2 odd number of ones only you will get output as high. This is the point. The next point, see here. The output is 0. When you get output as 0? If there are even number of ones in the input. See here, this case. 1 and 1. Total 2. 2 is a even number. That's why the output is 0. And one more case you'll get, that is, if all the inputs are 0, then also you'll get output as 0. So this is all about the XOR gate or exclusive OR gate. It is another form of OR gate only. Then next. Next we move on to XNOR. This is pronounced as exclusive NOR gate. XNOR pronounced as exclusive NOR gate. As in case of XOR, we are pronounced as exclusive OR gate. Now we are adding N here, that becomes exclusive NOR gate. So if you observe first the logic symbol of exclusive NOR gate, only one minor change you will get. See here, if you observe here, this symbol is exclusive OR. For this symbol, if you add not here, that becomes exclusive NOR. See here, just NOT gate is added for exclusive OR, that becomes exclusive NOR. Same thing, OR gate is there, for that we have added one curved line, that becomes exclusive OR. For that exclusive OR, if you add at the output side a NOT symbol, that is a bubble or a small circle, then that becomes exclusive NOR logic symbol. Then check out the input and outputs here. If A and B are the two inputs for a two input exclusive NOR gate, then the output what you will get is For according to OR, you will get A plus B. According to exclusive OR, you will get A plus B. That is, plus is circled. Then, if the A plus B circled one is input for NOT gate, then you will get A exclusive or B complement. It means A plus in a circle, B complement. Right? This becomes the output for exclusive NOR gate. For this two input exclusive NOR gate, if you observe the truth table here, see A and B are the two inputs, and A plus B, that is exclusive or B whole complement will be the exclusive NOR output representation. Then if you check out here, both the inputs are 0, output is 1. Both the inputs are 1, 1, output is 1, otherwise 0. How to state this? You see now. The explanation part you can observe now after knowing these two parts. See here. The exclusive NOR gate is complement of exclusive OR gate. The exclusive NOR gate, XNOR gate is complement of XOR gate, exclusive OR gate. XNOR is a complement of XOR gate. Then second point. The first point you can again confirm it. See here. 1, 0, 0, 1 you are getting in exclusive NOR gate. If you observe, see here, the XOR gate 0, 1, 1, 0. Exactly the complement of XOR will get here. Wherever you get 0 here, you get 1. Wherever you get 1, that will be 0 C if you are observing here. That's why the first point is the exclusive NOR is the complement of exclusive OR gate. Now, see here. Next point related to the truth table. The output of exclusive NOR is 1 only when you're reading output as high, only when the logic values of both X and Y is same. Either both the inputs, in case of two inputs, if both the inputs are same, then the output is 1, otherwise 0. See here in that statement, both the input 0, 0, output is 1. Both the input 1, 1, output is 1. In other cases, zeros. This is the point we are writing it here. Then, related to that only, its output is 0 when its inputs are different. See, if the inputs are different, some are 0, 1 is 0, 1 is 1, then in that case, if the different input means the output is 0 in case of exclusive NOR gate. In Boolean algebra, the circle with dot will get. This is wrong here. It is while copying, it is copied. In this circle, we'll get a dot. Here also, there is a dot here. Exclusive NOR is a dot. Right? Complement. So, see here, one input you can check out. A is 0, B is 0. If it is given for OR gate, then it becomes 0 only. But exclusive OR, so in case of this exclusive OR, if both are 0, output is 0. Right? This part is over. That 0 is input for this NOT gate. Then 0 becomes 1. That's why the output is 1. Take the second case and check. A is 0, B is 1. A is 0, B is 1. First take only OR gate, OR operation. 0, 1. What will you get? If it is a plus, 1 you will get. But in case of exclusive OR, 0, 1, 1. Right? Odd number of ones in the input is 1. Okay, that 1 is input for this NOT gate. That's why the output is 0. I hope it is clear. We're comparing both here, XOR and XNOR. Then check out the next operation, that is A is 1, B is 0 now. 1, 0 for OR gate. 1 plus 0 is 1. Exclusive OR gate, again, there also 1 because odd number of ones in the inputs, 1. If that 1 is input for NOT gate, then again output will get it as 0. Last input you can check out. Both the inputs are 1, 1. A is 1, B is 1. That 1, 1 are the input for OR gate. Then 1 plus 1 is 1. Right? You can check in the exclusive OR. If you add this arc in the input side, if both the inputs are 1, 1, output should be 0. If this 0 is input for this NOT gate, then the output becomes 1. That's why I said that this point, the XNOR gate is the complement of XOR gate. So this is all about exclusive NOR gate. So it means up to here we have completed the basic logic. First we have completed in the previous class and this class, that is what is gate we have completed. Then there are two different types of gates are there. One is basic logic gates and second one is derived gates. Under the basic logic gates we have completed NOT and OR basic logic gates. Then in the derived gates we have completed the first one, NOR gate you have completed, NAND gate you have completed, exclusive OR we have completed, then exclusive NOR gates. These 4 gates we have completed in case of derived gates. It means both the types of gates are completed. Logic gate types are over. Then after this, one more important part, that is the universal gate. After knowing basic and derived, the next heading what we are reading is universal gate. Normally we may get 1 mark question, name the universal gates. The NAND gate and NOR gates are called as universal gates. If you are getting a question on this universal gate, you can take care here, because if the question is name the universal gate means you can write NAND gate and NOR gate. Define or what is universal gate. At that time, you have to write the definition. That is this point, that is universal gate is a gate using which all the basic logic gates can be designed. This is the definition of universal gate. It means by using the NAND gate or NOR gate, you can design all the basic logic gates. What it states, this sentence, if you take NAND gate, the NAND gate can work like any of the basic logic gates. That is, it may work like NOT gate, it may work like AND gate, or even it may work like OR gate also. That's why it is called as universal gate. And in case of NOR also, if you take NOR, the NOR works like NOT gate, NOR works like AND gate, NOR works like OR gate also. That's why NAND gate and NOR gates are called as universal gates. So that's why the definition is universal gate is a gate, either it may be an AND or not, NOR, using which all the basic logic gates can be designed. Next, NAND gate and NOR gate are called as universal gates. What do we know now from the first 2 parts? NAND gate and NOR gates are called as universal gates. Why they are called as universal gates? The answer is because all the Boolean functions can also be implemented using these two gates. All the Boolean functions can also be implemented using these two gates. That's why these two are called as universal gates. I can say that using these you can design the basic logic gates. That's why they are called as universal gates. Then the next point. NAND gate and NOR gates are more popular as these are less expensive. See, one point is highlighted here. Why NAND gate and NOR gates are more popular? The one reason is this one, that is they are less expensive. And second point, why they are popular means, and they are easy to design. NAND and NOR gates are less expensive, one point, and second point is they are easy to design. Due to this reason, the NAND gate and NOR gates are more popular gates. Then next. So it means today's class we have completed the gates. Like we have started with today, the NAND gate is a combination of NOT and AND gate. That's why it is called as NAND gate. It is exactly the complement form of AND gate, because for AND we are adding NOT. That's why the NAND is the complement of AND gate, right? So in NAND is a short form for NOT and AND. It's a combination of NOT and AND. That in short we are calling it as NAND gate. And when you observe the logic symbol, just the NOT symbol is represented, added in the output side for AND gate. That becomes NAND gate. Then when you observe the truth tables, this truth table output is exactly the complement of AND gate. Here x dot y are in a bold letters, that it means this complemented form. X dot y whole complement is there. See here, in the previous case also I have taken this x and y, right? Then after that you have studied today XOR gate, exclusive OR gate, right? This is another form of OR gate. If you observe the logic symbol here, just for OR gate, one extra curved line is added in the input side, that becomes exclusive OR gate. That will be represented by just that plus is circled. Then when you observe the truth table of that particular gate, what you will get is, see here, the output will be 1 when the inputs have odd number of ones. It means we are counting the number of ones in the input side. If the number of ones in the inputs are in an odd number, then only the output of exclusive OR gate is 1, otherwise 0. That we learned here. After that we have learned the last derived gate, that is exclusive NOR gate. It means, again, if you compare this with exclusive OR gate, the XNOR is the complement of exclusive OR. XNOR is complement of exclusive OR gate. That's why for exclusive OR gate, one small circle in the output side, that is representing a NOT symbol, right? That becomes exclusive NOR gate. The output will be in complemented form of exclusive OR's complement is nothing but exclusive NOR gate. Then when you observe the truth table, what do we said that this is the complement of XOR. That's why the output will be high, output will be 1 when the inputs have both the inputs in two input no exclusive NOR gate, if both the inputs are same, then the output will be 1. Either both may be 0 or both may be 1, 1. Then the output will be 1, otherwise 0. After this, we have learned one definition here mainly, and 1 marks 2 questions may be arising here. That is, name the universal gates means we can write NAND and NOR gates are called as universal gates, and definition means define what are universal gates or define universal gate. Then you can write this one. Universal gate is a gate using which all the basic logic gates can be designed. So after knowing this,